introduction. Just wanted to mention that we will not have a lunch during spring break, but that's more than a week away. We just heard an exceptional ITC colloquium by Kochanek, one of the highest signal-to-noise ratio in the colloquium that we had recently. A lot of information. And Chris will tell us some more on other things towards the end of this lunch. By the way, if you noticed, we have a white tablecloth on this side of the table here, and there is a reason for that. We would like all of the students dining on this part of the table to join the astronomy department. And so please make a good impression on them and try to be nice. Not that you are not always nice, but we very much would like all of you to join us next year. And so we will start with Andra Stroe from the CFA, and she will tell us about cosmic tsunamis and tornadoes, galaxy evolution in disturbed environments. And then we'll hear from our own Michelle.
Ntampaka rhymes with Chewbacca.
Okay, so the way it's being spelled is Ntampaka.
Clearly the T and the P are silent.
Okay, so I received the wrong spelling, and that's why I had difficulty to say it. Okay, anyway, Michelle will tell us about the role of machine learning in the next decade of cosmology. And then we'll hear from Rob Garrod from Virginia. Where is Rob? Over there. And he will tell us about the microscopic simulations of interstellar laboratory ice formation. And he will also be the CFA colloquium speaker later today. And finally, we'll hear from Chris, who is spending a sabbatical here, so feel free to approach him later. We will talk about searching for non-interacting compact object binaries. Andra.
Thank you. Can everyone hear me? Great. Okay. So thank you very much for the to the organizers for inviting me to give this talk. It's the first talk to a wide audience of the CFA that I'm giving since starting as a CFA fellow, Clay fellow in December. So I'm a bit nervous, but hopefully this is going to go okay. You're a nice bunch, so it's going to be fine. So today I'm going to talk to you about some of the work that I'm doing, looking into galaxy evolution in extreme large-scale environments. And when I say that, I'm mainly thinking about merging galaxy clusters. So we know that clusters grow through mergers. It's one of the main ways. And mergers are extremely violent processes. There's, imagine two massive balls colliding into each other. And when they collide into each other, there's a lot of energy that's being released into the intercluster medium. And part of this energy is being released in the forms of shocks and turbulence. And this is very nicely illustrated here. This is something like a slide that I kind of stole from John Suhone. And this is putting together the bullet cluster in an actual bullet to kind of show what's happening when you have two of these clusters colliding. Imagine that the bullet is traveling through a dense environment, and then ahead of the bullet, you're forming this shock wave, and then in the backflow, you're getting all of this turbulence. So, there's a lot of interesting processes that are happening in these merging clusters, but I need to convince you guys that they're generally, interesting to study. And first of all, I will start off by pointing out that actually a lot of clusters are undergoing mergers. If you look at Sunyaev-Zeldovich selected cluster samples, about 50% of them, even at low redshift, are actually undergoing mergers. So every massive cluster in the local universe has undergone one of these amazing massive mergers in their history. So it's something very worthwhile to study if we are to understand the history of clusters in general. I mentioned that they have these massive megaparsec-wide shocks and turbulence. So they are actually the largest particle accelerators in the universe. But actually, the thing that I'm going to focus on today is what happens to the galaxies in these clusters as their parent clusters are colliding. So, our question was, we have these massive shocks that are traveling through the intercluster medium. Clearly, you detect them in X-rays, but at some point they pass through the galaxies. As they sweep through the intercluster medium, they pass through galaxies. So our question was, okay, when they go through the galaxies, do they do anything? Do they trigger star formation? Do they actually maybe blow all of the gas away from the galaxies? What happens? And we wanted to look at the different phases of star formation as well. So in order to see if there's any correlation between the time that the shock goes through the galaxy and the time scale for star formation. So in order to look at all of these phases, we want to look, first of all, at what is happening right now. What are the stars that are being formed right now? And with this, we're using H alpha as the H alpha emission line to select star-forming galaxies. We also want to see what's happening to what has happened to the galaxies in the past, maybe 500 million years ago. And for this, we're looking at supernova, so galaxies that have already exploded. And for this, we're using radio. And also, we want to maybe put in context what will happen to these galaxies in the future. And for this, we need to look at the gas reservoirs that could fuel future star formation episodes. And for this, we're using H1, so neutral hydrogen. And in order to investigate these processes, we went and we did a large survey of H alpha to select star-forming galaxies in a sample of relaxed clusters, but also massive merging clusters. And what we found was that if you just look at the number density on average of merging clusters versus relaxed clusters, merging clusters are overdense in star-forming galaxies. We don't really know exactly why this is. We checked for a lot of things. It's not caused by the cluster mass. Could it be that just the merger of the cluster somehow affects the galaxies in a different way? And in order to go into more detail, I would want to kind of highlight this amazing example of a merging cluster. It's called the sausage cluster. Do not blame this on me. I did not name this. But this is, it's a massive cluster. It's 2 times 10 to the 15 at a redshift of about 0.2. It's one of the most massive clusters at its redshift. And we think that it has undergone a massive merger happening in the plane of the sky, and we're now observing this cluster after these 2 subclusters pass through each other. And as they pass through each other, they form this massive shock waves that are travel outwards and that we are now detecting in the radio. So you can see here, this is a shock, and the one at the top is also a shock wave that we're detecting in the radio. And of course, the very peculiar shape of this shock in the north is what gave it the name, the sausage. I'm showing you here, so you see there in the gray, the X-ray emission for this cluster, and here we also have white lensing contours, and you see the cluster is definitely in a disturbed state in this north-south direction. There are 2 massive dark matter clumps, so clearly this cluster is merging. And we went and we gathered optical data to look at this object to select star-forming galaxies, as I mentioned, through the H-alpha emission line. In the background, again, you can see a radio image of this cluster, highlighting the location of the shocks. And all of these red circles that you see on the map are star-forming galaxies that we selected with H-alpha. And this particular object is extremely interesting. Its density of star-forming galaxies is about 20 times larger than an average cosmic field at the similar redshift. And not only is it more dense in star-forming galaxies, but these star-forming galaxies have different properties compared to field counterparts. What we found was that actually star-forming galaxies located in the hottest parts of the X-ray gas have very low electron densities, and it seems like these galaxies have contributions from supernovae and AGN driving maybe outflows. They are also more metal rich, so they do not they're not placed on the mass metallicity relation for their redshift, but it's actually elevated compared to field galaxies. So it seems like these star-forming galaxies are using generally more metal-rich gas to form new stars at all stellar masses. And the question is, of course, where is this more metal-rich gas coming from? And now we can think back of all of these maybe possible evidence for supernovae that we have. So maybe these supernovae have already pre-enriched the gas. So the idea would be that not only these galaxies in this cluster are forming stars at a very kind of good rate right now, but they seem to have been forming stars for a while now. And to tie all of this kind of evidence for supernovae from the optical to evidence that we have from the radio, we went and we, with very deep radio data, we looked to see whether we get detections of radio emission in cluster galaxies that are star forming. And what we found was that at a very high rate, galaxies in the cluster that are star forming have radio detections compared to just galaxies that are around the cluster selected with the same technique. So on average, galaxies around the cluster just seem to be coming, online, so to speak. They are forming stars right now, but they haven't necessarily formed stars maybe 500 million years ago. Whereas the cluster galaxies have been sustaining the star formation for a good while now. So the question is, how are they fueling the star formation? Maybe they already used up all of their gas at a very high rate, and now they should be, they should have used up all of it. So maybe they don't have a lot of gas anymore, so they won't be able to form new stars in the future. We were very surprised when we actually went and we observed this particular cluster with an absolute insane amount of time looking for neutral gas. I was very surprised to see that, redshift 0.2 for H1 is very, very difficult, but of course this will change in the future with things like DSK. But when we did this, we spent about, 2 weeks, 3 weeks of observing time on this, and we didn't get any single direct detection of H1. However, we did have all of this spectroscopy. We knew all of where the galaxies were, so we could actually use stacking. So we used stacking very effectively to get detections in galaxies that were selected in the cluster and galaxies that were selected outside of the cluster, both to be star forming. And what we found was that actually once you account for the slightly different average stellar masses of the two samples, cluster star forming galaxies have just as much neutral gas as their field counterparts. And this is a little bit surprising, I would say, given that you would expect galaxies in a cluster to have maybe a fixed mass lower neutral gas compared to field galaxies because of the stripping that's happening to them because of the interaction with the intercluster medium. So to put this all in kind of a nice package and a nice story, it seems like in this particular merging cluster, maybe in merging clusters in general, some of these galaxies manage to still hold on to their gas. And maybe as these shocks are going through, they're triggering star formation, and these galaxies start to form stars, and this star formation doesn't happen all at once. Simulations show that it can happen kind of in phases, and it can lead to sustained star formation for about 500 million years after the merger of the clusters and after the shocks are being produced. Of course, this is, putting shock-induced star formation out there is a very big statement. So I'm, definitely looking forward to talking to all of you, especially theorists, to see how we can explain these results that we're getting. And I'm right on time. I will just finish off saying that we believe that if you have gas-rich cluster galaxies, you can, in a way, rejuvenate them, make them start forming stars again in these mergers. So thank you. If you have any questions, please ask.
About these shocks is that usually a shock has a width of the mean free path of particles. In a plasma, it's a Coulomb mean free path, but the mean free path in a cluster is tens of kiloparsecs, so it's actually bigger than the size of the galaxy. And so there must be magnetic fields that are making the shock sharp, because otherwise it would not really be a shock as far as the galaxy is concerned. Did you think about that?
Whenever magnetic fields, they're always the most difficult thing. So definitely we're studying these objects in the radio, and in the radio we can, of course you don't get an idea about the magnetic field per se. For this we need very deep X-ray observations, but we can say something about, for example, the Mach number of the shock and all of these things. But in terms of simulations, I'm not aware of any simulation that actually has magnetic fields in it to see. So there's simulations that just put a shock through a galaxy without any magnetic fields, and it seems to do something. But there are no simulations, as far as I know, that have magnetic fields and all those things in there, which might change the situation quite a lot.
Well, in these simulations, they put by hand a sharp shock, but that is not physical. So one has
so this is definitely a case where they put the shock by hand. Ideally, I think we would want a simulation where you have realistic galaxies, but also having realistic galaxies in a cluster environment that's, many, many times larger. That is very, very difficult.
I think I should ask my question separately, since it's not an astronomy question. Well, I'll ask you. You had a list of co-authors,
Yes.
collaborators, and I noticed one name, H. Huckstra.
Yes.
A woman biologist at Harvard, Hopi Huckstra.
No, it's Henk Hoekstra. He's a specialist in weak lensing. So no, it's not a biologist, it's an astronomer.
Ramesh?
So in that image of the sausage shock, it looked like there were several galaxies that, at least in the plane of the sky, are almost at the location of the shock.
Yes.
So can you tell if any one of those has just gone through the shock, or the shock is going through it?
Yes.
And does it look any different?
Yes, so actually we have data that I need to look at as well. I have lots of data that needs to be looked at. So we have IFU data of a couple of these. So we actually want to see whether there's a difference between, a galaxy that's sitting here and a galaxy that's sitting exactly there. Of course, with only H-alpha, so we did this with H-alpha imaging, so we just have we can't really get a good distribution for the H-alpha gas, but with IFU we're hoping that we will see maybe some tails that are more pronounced and hopefully they're aligned with this merger axis. So, yeah.
It's really interesting.
Yeah, summer student project.
Have you looked at the radio spectral indices of your
Yes,
reactions?
yes. Yes, I do not have that here. You should have come to my cluster, this the talk that I gave where I explained all of this. Yeah, so definitely for this sort of object, we have many, many different radio frequencies. It's actually covered all the way from 150 megahertz to 30 gigahertz. And you can see a very nice spectral index trend in the radio going from the north to south. And you can also fit models to it, and that tells you what age the electrons have and all of these things. Of course, we need to make some assumptions about magnetic field because it's very far out, but it's it's surprisingly uniform. It goes, from flat to steep. I will show you later. It's really impressive, yeah.
Okay, well, let's thank Andra again.
Thank you.
Good afternoon. My name is Michelle Ntampaka. I was not joking. The T and the P actually are silent, and they actually are in there. And today I am going to be talking about the role of machine learning in the next decade of cosmology. This is a little bit different than a typical ITC lunch talk. Rather than zooming in and talking about one particular project, we're going to take a couple really big steps back and look at how machine learning interacted with cosmology in the past decade, and what I think that might look like in the next decade. And you have probably guessed that this has been submitted as a white paper, so I'm giving you a nice overview. So I'm going to start by asking the questions, what is meant by data science, and how does machine learning fit into that? So I'll read this. Data science is the study, the application, and often the art of creating and using sophisticated algorithms and cutting-edge data analysis techniques to extract information from data. And I really want to emphasize sophisticated algorithms. I think if you boil it down to just one idea, data science is using sophisticated algorithms. It's a very interdisciplinary endeavor. It combines or involves statistics and astrostats, applied math, computer science, and of course machine learning. There are also a number of things that data science is not, that it often gets confused with. So some things that fall outside of the data science definition: data storage and dissemination. These are important issues facing astronomy, but when a person talks about data science, they are not talking about dealing with data and archives. Nor are we talking about sort of standard data analysis techniques. So chi-squared, linear regression, I think really fall outside of what is thought of as data science because they're solid and established and easy to implement. They're not cutting-edge tools. Big data also falls outside of data science. I think this one surprises a lot of people. Of course, these things interact with data science, but they are not equivalent to data science. So when someone talks about data science, they are really talking about the sophisticated algorithms. Okay, I want to focus on machine learning. So let's take a minute and define that. So machine learning research explores the development and application of algorithms that find patterns in data. In astronomy, what can we do with machine learning? Things like describing complicated relationships in parametric or non-parametric ways. Can identify data clusters. I don't mean star clusters or galaxy clusters. I mean chunks of data that are similar. And also identify interesting outliers. Reduce scatter by using complex or subtle signals. You can generate simulated data, often faster than traditional generative approaches. Classify objects, address sparse data, and explore data sets to understand the physical underpinning. And in a moment, I'm going to show you examples of 3 from this list. But first, I want to show you how machine learning is gaining traction in astronomy. So here is refereed astronomy papers with the phrase machine learning in the abstract. Not a perfect way of testing this, but it shows that over the past kind of 10 or 15 years, we've really seen a significant uptick in research that pulls from these 2 domains and combines them in a creative way. And from what I've seen from Cosmology, kind of right around 2014, 2015, 2016, you start seeing machine learning methods that use phrases like a factor of 2 improvement or an order of magnitude. So I think very recently we're starting to see really new machine learning techniques that are making a big difference in the state of the art. So as promised, here are 3 examples of machine learning questions, machine learning techniques applied to cosmology questions. Shameless self-citation on slide 1. So this is 2015 and 2016 papers that look at machine learning mass estimates from galaxy cluster dynamics. What you're seeing is a PDF of errors. And the method, support distribution machines, is a distribution to scalar regression technique. At the time that this paper was published, it was fairly new. It was a year or 2 old and was able to reduce errors in cluster mass estimates by about a factor of 2. This is a more recent paper that generated n-body-like simulations using deep neural networks. What you're seeing in this image is errors compared to a full expensive n-body sim. So the images that have a lot of green and yellow are the ones that have more error, and the ones that are more white have less error. On the left, you're seeing a Zeldovich approximation. In the middle, 2LPT, which is a fast n-body-like. And on the right, the deep learning method. And what's really remarkable about this is that it can generate these n-body-like simulations with positions and velocities in 30 milliseconds. And the last one that I want to highlight is a classification method. This one was galaxy scale strong lens classification with deep residual neural networks. And this method entered a competition and outperformed what I think many of us would consider the gold standard, which is human classification. So this one actually did a better job at identifying strong lensed images than a group that I think actually just looked at all of them. I think they may have actually stayed up all night to get in the time window that was allowed. So what's next? What will the next decade look like for machine learning in cosmology? I think there are a lot of opportunities. There are big data opportunities. LSST, HERA, SKA are all going to produce unprecedented data volumes, and there are going to be tremendous opportunities for us to use new methods on those data. Pipeline optimization, things like identifying transients in real time for follow-up is going to be a really important question that I think will best be addressed by machine learning. There are low signal opportunities. I personally am really looking forward to getting my hands on the high redshift eRosita clusters, even though some of those clusters will only have order of magnitude 100 photons. And archival data. There is evidence that there is still information in our archives that with the proper data analysis techniques, we can get more information out of. As far as up-and-coming methods that I see, when I attend conferences that are more on the machine learning end of things, generative adversarial networks seem to be really hot right now. A generative adversarial network is actually two networks that play against each other in a zero-sum game. One of them tries to generate fake images that will pass as real, and the other one, the discriminator, tries to tell the difference between the real and the fake images. So when you train them against each other, there's a real power that helps them to become more robust, and then you can pull those two pieces apart to do separate tasks. I think machine learning interpretability is also another issue that cosmology and astronomy will need to confront over the next decade. So at my last lunch talk, I talked a little bit about Google Deep Dream, which takes an image that is originally classified as the Crab Nebula and turns it into this. So it's like a dog here, kind of a giant chicken, and if you look very closely, there's a spider web up in the corner. So you change the classification of this image from something that it really is to something that it very much is not. And I showed that you could apply such a tool to something that has a physical underpinning and try to understand what is going on in the physics underneath. That being said, I think that there will always be tasks that require human ingenuity. These are not them. The first time that I saw this, I was told that they were actually failure modes of machine learning, but I have since learned that this is just a meme. This one's my favorite. Labradoodles and fried chicken. All right. And rather than finishing with a questions slide, I want to put up some resources for getting started with machine learning. The first one, I think that one of the real barriers for pulling in machine learning to astronomy research is actually just becoming familiar with the vocabulary and the words that feel very familiar but are used in very unfamiliar ways. And this machine learning crash course by Google is a really phenomenal way to not only learn the vocabulary, but also to get sort of an intuition for some of the methods that are out there. If you email me, I can send you these things, or I could just spam everybody at the CFA with it. Scikit-learn has a really nice flow chart for identifying an algorithm for tackling a problem. If you have a problem in mind, that would be a place to start. And the book that I have up there, I think, is really nice for talking about proper ways to deal with methodological questions in machine learning. And with that, I will stop and open to questions.
There are many things we can learn from Michelle, one of which is how to give an exceptional presentation, because everything was clear and there is a reason for that. Michelle used to be a teacher.
That's right. I started with 6th graders, moved my way up to high schoolers, then parked at the university level for about a decade before deciding that I really loved the science too. But that being said, I'll use this to advertise that if you ever need a speaker for your group meeting, I love talking. You wouldn't have to twist my arm very hard to get me to come to the talk.
Well, we just hope that we are better than your previous students. One question, one data set that would be very interesting to look into is LIGO, because they released 10 events that are high signal to noise and very clear, but I wonder if you apply, is anyone applying machine learning to the data sets they have?
I don't personally know, but I see nodding, which suggests to me yes.
Elu Huerta at NCSA has been doing a lot of work on machine learning in the library.
Did they discover new events?
I don't think so. They've mostly just been able to reproduce the current match table and stuff, but I mean, it's also early days. Well, the IAS one isn't machine learning. That's just
Okay, it would be nice to see the superiority of machines relative to humans at some point. Erwin?
I was wondering if Gaia uses any machine learning techniques, and if not, do you think they should?
The answer to the second question, regardless of the telescope in the first question, is yes, I do think that they should. Again, I don't have personal knowledge, but I'm looking around the room and I'm seeing nodding. So I will use my advanced data science methodologies to give you a yes on that question as well.
So you showed these examples, and the second one was this simulation.
Mm-hmm.
So if did I understand this right? You give your neural net the initial conditions of the universe. It predicts the evolution, and you compare it to the real n-body simulation, and they are practically the same.
One tweak to that statement,
Yeah.
not the initial conditions. I think they actually gave them the Zeldovich approximation.
The Zeldovich approximation comes from the initial condition.
Sure.
Anyway, yeah.
Sure.
But that's amazing. So we can stop doing n-body simulation.
No. I don't think that's the space either. Just as 2LPT provides a kind of quick but not totally accurate way to do n-body, I think this is the next step in that progression. I don't think that it completely replaces n-body. I think that talking to the authors of that paper would be a better place to get proper information on that. I don't think it's time to stop doing n-body simulations yet. But if you have a task that requires a large number of simulations that is just not tractable, that you would have otherwise turned to 2LPT to generate the simulations, I think that this is another alternative that may have strengths over 2LPT.
So a question about the possibility of using tools like this to find something that you're not looking for.
Mm-hmm.
So, for instance, my own experience is dominated by Michael engine, where we found these rare events. And we basically learned that we could find a needle in a haystack because we knew what a needle looked like. But we didn't do anything remotely like what Jocelyn Bell did with crummier data, finding radio pulsars. She was just a bright graduate student looking for one thing and noticing something else. And is that going to be part of this story, or is it still going to be learning how to do what we already kind of know, but better?
So there are two kind of different areas of machine learning. Supervised is where you kind of know the answer, and you know what you're looking for, and you can simulate and label some data. Unsupervised learning is where you don't have labeled data, and you are more looking for interesting groups of data or interesting outliers. And if I was going to try to tackle a task like that, I would first head to unsupervised learning as a way to find outliers. Now, outliers to machine learning are not necessarily outliers to physicists, so proceed with caution. But that is where I'd start as far as advanced algorithms are concerned.
Maybe we should apply the same to the education of our graduate students. Let them be unsupervised and see what they find. And if, after that, we can supervise them.
There is always space for some academic freedom. Yes.
Let's thank Michelle.
Okay, well, so firstly, thank you for the invitation to come and speak in the colloquium, and obviously to speak now on this sort of somewhat hastily gathered together little talk. So what I want to talk about is simulations that we've been doing in my group for several years now, not just of interstellar ices, but the experiments that people do in the lab to try and understand the formation and the behavior of those ices. So we're trying to sort of simulate both in an effort to bridge the experiment and the observations. So this may be a surprise to you or not, but there is ice in the interstellar medium. So it is formed on the surfaces of microscopic dust grains. Okay, this is an interplanetary dust grain, but we think sort of morphologically interstellar dust is not so different. The canonical sizes of these grains is about 0.1 of a micron. When you form ices, the typical dust temperatures are somewhere around 10 to 20 Kelvin, so extremely cold. We form ices of about 100 monolayers maximum. Okay, so the ML here is not machine learning, it's monolayers or molecular layers. So just imagine sort of 100 water molecules sort of stacked up on top. That's the kind of image we have. So we form these ices in lots of different regimes. The typical one that I've put in bold here is in quiescent interstellar clouds, because they're just easier to study from this point of view. There's not so much sort of violent activity going on. But we see, observe ices in lots of different sort of interstellar and star-forming environments. So these ices are actually detected through infrared absorption observations. This 2 to 20 micron band is a typical place to look for these absorption features. So the ices are mostly composed of water, but they have a lot of other stuff in them as well. So there's a lot of CO and CO2. Both of those are on the order of around 20% of the total ice. But there are other simple hydrides other than water, so methane, ammonia, methanol, and so on. There are some other things, but it tends to be these small ones that we can identify most readily, because in the infrared, we're really observing functional groups rather than a whole molecule. So I will say a couple more sort of things about the background. You should just bear in mind what the time scales are here. So we're forming these ices very, very slowly in the interstellar medium, on the order of 100,000 years or so. Okay, so this is a very, very slow process. The mechanism by which we think that the interstellar ices are formed is the addition of hydrogen atoms to oxygen or CO or other atoms from the gas phase. Okay, so I've highlighted this reaction with CO. But it's more or less hydrogen moving around on the grain surfaces. So this is something that we started to simulate microscopically a few years ago in my sort of my research group. So this is a preliminary and very simplistic model of this hydrogen diffusion process on the surface of a cold grain. Okay, so you see a hydrogen atom hopping around. There's an oxygen there that just got hydrogenated. When the hydrogen meets that atom, they're both very reactive and they form an OH radical. And then eventually this other hydrogen atom will find that OH radical and will form water. Come on, hydrogen, you can do it. There we go. Okay, right. Okay, good. So this is a sort of a thermal process of hopping. We have these other events and so on involved. So I'll tell you something about how this model works in a second. But if you do this type of simulation for a long time, you can build up these very thick ice mantles. And this is perhaps, well, we're not quite sure whether this is a very accurate representation of true interstellar ices, but in these models at least we see this very sort of amorphous creviced structure that I think I will sort of move on from in the interest of time. So I'll say something about the model. So this is what's known as a kinetic Monte Carlo model, but its unique feature in the field is that it is an off-lattice treatment. That is to say, we don't assume any initial structure. We don't assume where particles can go. We sort of trace the positions of all the particles on the fly as the simulation goes on. So this is all randomized. So all the trajectories of incoming particles are random. It is obviously not completely random. We calculate the sort of relative rates of different processes, but we choose between them randomly. So the surface binding of particles onto that, this is a sort of blow-up of that same grain. The binding is a van der Waals type, so this is a physisorption type binding, not chemical adsorption. So these are all pairwise potentials. So when we calculate the binding of, let's say, a hydrogen atom to that surface, we're looking at all of its pairwise interactions with the surrounding partners. Okay, these are short-range potentials, so we sort of cut them off at some sort of appropriate range, and that makes the calculations a bit easier. So I think the main point to make here is the position of the particle is determined by the position of the potential minimum locally on that surface. Okay, so that's what makes this an off-lattice model. Okay, so I'll skip that. All right, so the evidence for this porosity, or this sort of amorphous structure in the interstellar medium is actually a little sketchy. So in the lab, we can see some very porous, these very amorphous porous structures with porosities often as high as 50% if you form the ices in the right way. Okay, so we'll form these ices maybe as low as 10 Kelvin. And typically in the lab, you don't form the water on the surface, you just dump water molecules from the gas phase at low temperature, and they build up and they form this ice. Okay. In the interstellar medium, as I say, there's no really direct evidence of porosity. One way of detecting porosity would be to look for this so-called OH dangling bond mode. I forget how many wave numbers it is. I don't remember wave numbers, but it's about 2.7 micron. Okay, there's no evidence for that dangling bond mode in interstellar observations. So we've got no clear idea of how much porosity there is, at least in interstellar water ices. But if that porosity exists, as we see in the lab at least, then you could fill those pores with other molecules, more volatile molecules like CO, for example. That's certainly an idea that's been put forward. In star-forming regions, for example, we have a warming up of the ice, and this material could then sort of be released from the pores later on. Okay, so what we're trying to do in our most recent simulations is to model the lab experiments in such a way that we can really pin down our treatment of the microphysics so that we can then extend those models to interstellar ice production. So this is what we did here. This is a simulation. So here, rather than using an actual three-dimensional grain, we instead use a flat surface with periodic boundary conditions. So that's what we're looking at here. And if you see that there are different temperatures along the top here, that show you the temperature at which we're dumping water molecules onto the surface. Okay, so at very high temperatures, you get these very smooth ices being formed because there's a lot of diffusion of those water molecules. So they have enough energy, they can just thermally hop around and find local potential minima, so essentially little holes in the ice, and fill them in. So we get very smooth ices. Okay, the typical sort of lab deposition rate is this central row here. So that's the one we're going to concentrate on. And we can compare these data. So these are pictures, of course, but we can determine densities from this fairly easily. And so we can compare those with what you get in the lab. Okay, so the lab data, so it's not my data particularly, but it's just old data. So these arrows show you the density behavior with deposition temperature. Okay, so I'll try and be very quick here. So what we see is our model, this one, has a very nice agreement with the experiment at high temperature where we're in this thermal regime where there's a lot of thermal diffusion. Okay, it behaves very nicely, but it doesn't behave very well at the low temperatures. Okay? So what we infer from this is that there is a non-thermal diffusion mechanism that we are missing in these models. So what we did in our paper, and I should say this is my grad student Aspen Clements did this work, we put in an essentially a very generalized mechanism to take into account, I'm not going to sort of walk through this because the buzzer just went, to take into account the excess energy you have when the particle is adsorbed onto that surface. So it's going to be accelerated into a potential very close to that surface, and that gives it kinetic energy. So that it can potentially diffuse non-thermally immediately after it adsorbs. So that's what we did. There are sort of two parameters in here that are essentially energy efficiencies, how much energy is retained on collision, and then how much is retained on subsequent diffusion events. So essentially as that energy runs out. So what we found is, so we ran a sort of a small grid of models for these two free parameters, and we found the best match to reproduce the experiment. So this is what these things look like. This is our best match. So at 10 Kelvin and 130 Kelvin, you can see very different behavior as these things build up. There's just much more diffusion in this sort of high temperature regime, but there's enough diffusion at the low temperatures now to reproduce the experiment. So this is what we see. So this is the old version, and now we actually get, this is our best fit model, we actually get very good agreement in the entire temperature regime. So summary of this work then. So I want to impress on you again, we need to use these models to sort of unite the data from the lab and the interstellar medium. It seems like actually only 1 or 2 extra non-thermal hops following adsorption is sufficient to reproduce the experimental results. I think we're gaining confidence now that actually we can reproduce these well enough that we can move to rather more complicated mixtures and experimental techniques and try to model those. Okay, I will leave it there. Thank you very much.
Are there any direct measurements of dust, interstellar dust from the outer solar system that we can probe dust directly with?
Sure.
In principle, Voyager 1, Voyager 2 went out of the heliosphere and they're meeting interstellar dust over there. But I don't know if there's any probe that analyzes the dust.
I really don't know. Oh, sorry.
There are plane detections of solar dust grains.
Here, I mean, locally.
Spacecraft.
From spacecraft. It would be another way of figuring out what happens in the interstellar medium rather than laboratory experiments or theory.
Yes. Well, the lab experiments are still easier than the solar grains.
You mentioned towards the beginning that the time scale for the formation of these ice grains and stuff was 10 to the 5th to 10 to the 6th years.
Yes.
I was wondering on what that range is based. It seems to me it would depend on the temperature of the surroundings, the density of various components, and so forth. And I was wondering to what extent this was a theoretical range and to what extent it had some experimental basis and what kinds of assumptions were behind it.
Yes, so it's a theoretical range. It's mostly based on the rate of oxygen accretion onto dust grains. And there will be some variation in those rates depending on the size distribution of your grains, for example. And you mentioned density, I think. Yes, the gas density is going to make a difference. There will be some threshold density at which the density is high enough for these atoms and molecules to stick to the surfaces rapidly, while the temperatures are low enough for them to remain on that surface. So that combination of the dust temperature and the density actually constrains this system sufficiently that I think my 100,000 to a million year estimate is more or less what all the models suggests.
Just so I understand, your modeling is based on the deposition of water molecules, but I think the evidence is that most of the water on grains is actually formed on the grain through the process you were just alluding to. Oxygen hits and then hydrogen finds it. So I'm curious how that changes the results that you're getting, if you don't start with a fully formed water molecule. And also, I was curious that you were showing still what appeared to be a rapid buildup of water ice on these molecules at 130 Kelvin. The sublimation temperature of water from a surface begins to go up rather rapidly, around 90 or 100 Kelvin. And I'm just wondering whether that's in what you're showing us. I would have expected water to be disappearing rapidly.
Yes, well, it is formed in the lab at those temperatures. So it's completely in agreement with the lab data. I guess it's some function of the rapidity at which you deposit. If you throw molecules rapidly enough at that surface, some of it will stick, and at that point you've changed your surface to a primarily water surface, and then that water will build up nicely. Your point about the formation of the water through atomic addition, that is entirely true. I completely agree, yes. What we're trying to do here is reproduce the experiments first and get these sort of microscopic treatments well understood based on the experimental evidence that we have. There is experimental work done on atomic addition reactions. We are working on models to do that and to compare those, but we're not at a stage where we can present that.
Thank you. Since water is very important for life, we are grateful for the work that you are doing in trying to explain our roots, so to speak, in the interstellar medium. Thank you very much, Rob.
Okay, so as came up several times in the talk I gave earlier, there's this unpleasant fact that stars like to have friends. And in fact, massive stars like to have lots of friends. And we've seen Roseanne here, but in Roseanne DiStefano's synthesis of a lot of the binary data, the number they get is something like 84% of massive stars are in binaries or more. In fact, a lot of are in triples or quadruples as well. And so basically, almost all studies of stellar evolution and passage to supernova are for single stars, whereas basically almost none of them are single. And so the question then is, well, how do you find things which still have companions? And there are surveys for binary star systems as stars, but if you ask how do we find them once some of them have turned into compact objects, at present there are really only two ways. One is, as illustrated by this cartoon of SS433, is you dump material onto the compact object. The other new one is you could look for mergers. But in terms of getting to these things, you go and find someone's paper on how to form one of these things, and this is for the neutron-star LIGO merger, and you get this. Okay? And a number of these is your word for today is sausage. There's a lot of sausage making going on here, and things which are poorly understood, like common envelope. And if you go and ask what's coming out of LIGO, it's less than 1% of initial binaries will ever actually merge as LIGO sources. And so it's a very, very biased sample you're going to get. And similarly, the fraction of binaries which are going to be interacting is also a very small fraction. And so the question is what can you do to do some more information of a census of things which are binaries or compact object binaries, which then might let you better constrain all of these intermediate steps which you have to go through in the end to have any really fundamental understanding of, say, LIGO mergers. So there are a number of ongoing surveys trying to do statistics of binary stars. So that's actually not on too bad a ground. And less good are surveys trying to deal with triples and quads, other than knowing that a lot of them are triples and quads. There are, of course, surveys for compact objects, right? We know of lots of HMXBs and LMXBs because they're bright in the X-rays and they're fairly easy to find. But you don't really know quite how to use them for statistics. Similarly, with pulsar timing, you can find non-interacting binaries, but in general, people don't try to use pulsar binary statistics for statistics. So the question then is how much you might do this. So for example, one thing you might really like to know is what fraction of binaries survive supernovae. So if you have a binary and you explode one of the stars, the binary can be disrupted for two reasons. The first is simply the mass loss. Right, is if you have a binary and you eject half of the mass, the binary becomes unbound. If you retain more than half of the mass, it remains bound. And then the other thing which became clear once people started seeing pulsars and their fast motions is that at least for forming neutron stars, there are also kicks of several hundred kilometers per second imparted to the neutron star and its formation. And obviously, if you kick the neutron star by 300 kilometers per second, it will become unbound. And so a fundamental number for any of these sort of binary population synthesis studies is just what fraction of binaries remain bound after a supernova. And it would be nice to do this observationally. And you could do this sensibly if you look in supernova remnants. And the reason you want to look at supernova remnants is you can plausibly do a complete census of at least neutron stars and supernova remnants, because you can find them. It doesn't have to be a pulsar beamed at you. It can just be a pulsar, because they produce what are called pulsar wind nebulae, so you don't have a beaming issue. And you can also just find them from their thermal emission if they're young enough. And so you could plausibly find in nearby supernova remnants all the neutron stars. And then you could go and ask as well what fraction of them are in binaries. You can also try to ask what fraction of them have become unbound binaries. So unbound binaries are hard because you don't know where to look. And so you go and look at the center of the supernova remnant, and there are, 50 stars. And then your problem is to figure out which one of those stars might have been an unbound binary companion. It turns out even in the era of Gaia, that is hard. And the reason is Gaia gives you nice distances to the stars, but you don't know the distance to the supernova remnant. And so if you knew distances to supernova remnants accurately, then Gaia would be brilliant for this. But without corresponding accurate distances for the remnant of the compact object, you're in trouble. But you can do it for the very young ones. For Cas A, the region you have to search for a disrupted binary companion around Cas A is about 6 arcseconds. And there is no star within that 6 arcseconds. And so for the 3 young supernova we know about, none of them were binaries at the time of death. Okay? What is interesting, and so much surprise hadn't been done, is no one had actually just gone and asked how many of these compact objects were in bound binaries. This turns out to be really simple because you know where to look. The sample we did is you could look at about 50 supernova remnants, which contained, 23 compact objects. And it turns out in this sample there are 3 binaries and they're all interacting. One of them is SS433, and 2 of them are neutron star pulsars in a wind, and so they're wind-decreting systems that are producing gamma rays and X-rays. And there are no non-interacting binaries in the sample you could look at. Okay, and so it's our first attempt, but you can get that less than 10% of supernova remnants contain a non-interacting binary, and something like 8% contain interacting binaries, which is the sort of number you need to better pin down the sort of population synthesis models. The big problem here is it sort of looks like people kind of gave up on trying to do censuses of compact objects in supernova remnants. And so there are a lot of these where people got frustrated because they would look at the X-rays and there were faint X-ray sources, but they had too few photons to figure out which was a background source and which was a foreground source. And I think everyone finally threw up their hands and went home. But you could do better on this. Okay, but what about non-interacting binaries in general? We really just don't know the abundance of neutron star or black hole binaries which are not interacting. And fortunately, the SDSS Apogee survey, and also LaMost and other things can also do this in theory, gives you a way of trying to do this. So the Apogee survey took infrared spectra of something like, at this point, 200,000 stars. In an SDSS-5, that's going to go up to several million. But as part of their strategy, they deliberately did not acquire their spectrum all at once. They would acquire their spectra in chunks. And so for every one of these stars, you essentially have a very sparse radial velocity curve. And so We did one version, and then Adrian Price-Wayland, who was here, but I think is now left, was doing it another way, is what we did is we took everything which showed a sign of a radial velocity variation. Then we got light curves from our assassin survey and looked for ellipsoidal variation, so we had a period. And then we classified everything by mass function. Okay? And so then you go and look at the things with the highest mass functions that show no signs of a second star, okay, in the spectra or the light curves. Or what Adrian did is Adrian focused on these small fraction of these stars in which they had many more radial velocity measurements than usual. And so he looked at things where you could better constrain things directly. Okay, and so out of this, the 100,000 we looked at, we found one very interesting candidate. So here it is, this is the mass of the star. So most apogee stars are giants because of the way they're selected. They're red giants. And here's the mass of the companion. If you model the spectral energy distribution of this star, it looks like it is a 3 solar mass giant. Okay, so the luminosity of the star says it's basically in here. Here are lines of inclination. And so if you look at what the mass of the companion is, nominally, it actually wants to be a nearly edge-on, roughly 3 solar mass companion. For various reasons, edge-on is favored over more tilted. And which is interesting because actually, while it's allowed, it kind of sits very close to the boundary people have between minimum masses of black holes and maximum masses of neutron stars. If this mass is right, you can ask is, can I have a 3 solar mass companion and hide it? Okay, so here is the SED of this star. So in wavelength and energy per unit wavelength. And there's the photometry you've got. And so here is even what you would get for a 1.5 solar mass star. And if you try to put a 3 solar mass star, you may have heard that luminosity increases a little quickly with mass, and so a 3 solar mass star will be booming and trivially detectable. And so this looks like a reasonable candidate for something which does have a non-interacting companion. In this case, it's a little bit of a cheat, right? Because we did look for it for ellipsoidal variability, and so it's not accreting anything as far as we can tell, but it is enough to distort the companion. And so the game we're doing now is we have a list of, I forget the exact number, it's like 50 other candidates where in fact we're using the 60-inch to try to fill in more of the radial velocity curves to find more of these. And this could be quite a growth industry because, as I said, as apogee, this is partially focused SDSS5 interest in doing apogee to get better radial velocity curves in the next generation. And so you could be able to implement this across 100,000, a million stars instead of 100,000, and with more design into the survey to try to do this, rather than it's sort of being an accidental property of the survey. Other than that, you're sort of stuck, because the only thing which can actually do a good survey of the black hole mass function is WFIRST. Is that WFIRST microlensing program is probably the only thing which will ever actually give you the mass function of black holes. But that's 15 years off, 10 years off before you're going to have any data. Okay.
Chris, since you mentioned that triples and quadruples could be quite likely, would that, given quasi-Lidov oscillations and things like that, they could change the census quite
Yes, it does. I was running those simulations yesterday.
Oh, okay.
Yes. Triples are the new doubles, so people haven't even caught up on the doubles, so triples is kind of pushing them over the edge. And then the quadruples will be even more interesting, right? Because in some cases, when you take the triple system and you're essentially disrupting the binary properties, you can start to get some of the effects you see in like when people simulate binary star interactions in globular clusters. Okay? It's a little bit weird because you start from a balanced system, so they don't act quite the same way. But an important property of that is if you look at the interactions, basically a binary has a much bigger cross-section for interaction than a single. And so if you do the triple and disrupt it, you're going to interact with a binary with a single. That will have less room for doing exciting things than if you do it in a quad, because now you have a binary interacting with a binary. And so essentially their interaction cross-sections both go up. So quads will be even more exciting than triples. But you do get many of the same things you see in the old globular cluster things. And so sometimes the neutron star emerges attached to its original binary. Sometimes it trades off and wanders off with the tertiary. Sometimes the surviving stellar companion wanders off with the tertiary. And the problem with the Kozai thing is what you get depends a lot on what you put in for the initial conditions. So if you have to put in that the initial, so it's a hierarchical binary, so you put the massive star as companion, the massive star is going to explode when you're at a tertiary. So you do anything sensible, you have to set that up so the hierarchical triple and is at least relatively stable. But if you add the further criterion that the pre-existing binary has a Kozai time long compared to the evolution time, then you generally get that the post-explosion binaries or triples have Kozai times that are longer than any reasonable lifetime for the next explosion. If you allow Kozai to possibly occur before you do the first explosion, okay, then it's no longer a self-consistent model, but you frequently get that Kozai will matter after the explosion as well if it stays bound.
Any other questions for Chris?
So Chris, I want to go back to the first part of your talk, the statistics, right? So most massive stars are in binaries, but if you go and look at the supernova remnants after the explosion, 3 out of 3 do not have a disrupted binary, and 10% or less have a bound binary. So what's happened to the other 90%? Because if they all have started off as binaries, shouldn't it be either unbound or a bound binary at the end?
So there are a bunch of issues. So the first thing is that like a third of all the binaries you start with merge. And so when they explode, they're actually single stars, all the models of 87A. Second thing is, right, you're really only sensitive to compact object star binaries, whereas a fair number of your supernova remnants are actually the second explosion. So you get dilution by second explosions where either the binary is already gone or it's the other companion is a compact object and you have no way to look for it. And so in at least the version of the population synthesis models we used, which were consistent with this, it's something like 30-odd% of remnants should have an unbound binary companion, and something like 10% should have a bound companion. And the numbers we got, I mean, it's, plus all statistics is not very much, are okay with that.
But it still won't be okay.
Yeah. The other interesting thing is in digging through this literature, by the way, never, ever work on the literature of supernova remnants. I warn you now, don't do it. If you want to collect the data on a single supernova remnant, it's spread across 5 papers. And those 5 papers do no other supernova remnants. So to do 50 supernova remnants, you have to look at like 200 papers. That was a bit of a nightmare. But there was an interesting and quite dangerous trend in some of these papers. Is you would find that people would reject things as possible counterparts because there was an associated star. But an obvious and demanded statement about all of these binary evolution is that in many cases the compact object should be associated with a normal star which it is not interacting with. And so it was a little bit tricky to figure out how to deal with this little bias you found in drifting around these papers.
Okay, well, we got to our time limit, so let's thank Chris and everybody else.